Yeah. Okay. So I thank the organizers for inviting me. Yeah, and this is some work together with Gandalf Lechner. And as I will try to explain to you, it is inspired partially by some themes in non-commutative geometry. So I hope if that works. No, it does not. So I have to go. Okay, so let's first look at a linear hyperbolic partial differential equation, df equals 0, where d is here a linear hyperbolic differential operator on Minkowski spacetime. You see it has a metric principal part and then some lower order terms. So the coefficient functions can be a general smooth function, and they are matrix valued if we allow n components for the field. Yeah, and then I should remind you that if you have such a differential equation, there are unique retarded and advanced fundamental solutions, and we use the general notation R plus and minus for advanced and retarded fundamental solution. So if you have some compactly supported n-component smooth function, then what they do, they, well, when you apply the differential operator on fundamental solution after function, you get the function back, and assuming sufficient symmetry of the differential operator, that works also if you exchange the order. So here h is C0 infinity, and these advanced and retarded fundamental solutions are distinguished by their support properties. So you have that the support of R plus or minus on H is contained in J plus or minus of the support of H. So, and if you do not so often live in the Lorentzian world, then I should tell you what that is. So here you maybe have the support of H, and now we think of that as a dimensionally reduced Minkowski spacetime, like so maybe. So time goes vertically up. And then what's in this future causal shadow, that is J plus the causal future of the support of H. That's all this here. And then similarly, you can have J minus, would look something like that. J minus the support of H. Okay, so that is very well known, very well established, and you can look it up in nice books. And okay, now what we want to do is something different. So we consider a linear hyperbolic partial differential equation plus a non-local potential. So we have D as before. That's the nice hyperbolic partial differential operator. And we add some term there called lambda times W. So this lambda is a parameter, which I will tell you about later. And now W is not a potential which acts by pointwise multiplication of on the functions, but is more general, can be a linear operator mapping functions to functions. And in particular, it can be non-local, so it need not preserve the supports of the functions it acts on, or it might even destroy compact supportness of functions. And what is important, even in time-like direction, we know when you are looking for solutions of such a equation, like up there, if the potential is non-local in the spatial directions, then this is not so tragic. That's not very serious. You can still deal with that with standard methods. But if you have a non-commutativity in the time-like direction, then things become complicated. And as you already suspect, you will have a difficulty with something like the Cauchy problem. Okay, so let's look at that in a little bit more detail. And now I'm missing the rest of the file. This is not good. So I try. That's up there. Open the one up there. Yeah, this one. Okay. Well, maybe try it like that. Okay. So, yeah, I already told you about the well-posedness of the Cauchy. Well, this I did not tell you, but that's a consequence here of the existence of the unique, advanced, and retarded fundamental solutions. And now I'm already giving you the take-home message. For lambda sufficiently close to 0, the non-local linear hyperbolic partial differential operators can still have unique, advanced, and retarded fundamental solutions, provided you impose sufficient regularity on this W term, of course. But in general, the Cauchy problem of the non-local linear hyperbolic PDE is in general ill-posed. So I will now give this a little bit a motivation I will come back to a little bit later again. So motivation is, well, interaction with an external potential is always a nice problem, and you can model various physically relevant situations in that way. Now what happens if, let's say, we have in mind a quantum field interacts with a non-commutative external potential? It's scalar potential in this case for the simple situation. So instead of pointwise multiplication with a function as the action of the potential, you can have, well, you replace it, let's say, by the Moyal product. And maybe where the deformation matrix has full rank, so it really does something non-commutative with the time as well. Well, such operators can approximate it by integral operators which have a C0 infinity kernel. So what we will look at is such potential terms where the interaction operator is given by a C0 infinity kernel. That's the easiest situation. If you think of this non-locality. Now, things can be very non-local in the domain and range of W. But on the other hand, W is now analytically very well behaved. Yeah, it's a smoothing operator. Okay. So, and I already give you the main result here. So let this d lambda be the hyperbolic operator plus lambda times C0 infinity integral kernel operator, as you see there. And assume that D is pre-normal hyperbolic. So hyperbolic I have explained, yeah. Pre or normal hyperbolic, it rather was. Pre-normal hyperbolic means it can be something like a Dirac operator. So D is pre-normal hyperbolic if there is another operator, D prime, let's call it, so that D prime D and D prime are normally hyperbolic. And both are first order. Yeah? So both first order. Right. So the Dirac operator would be a good example. I have presented a D which is second order, but it can also be first order as long as it's pre-normal hyperbolic. So everything holds in the same way. But for simplicity, I usually think of the hyperbolic situation. That is what I had presented before. But it also holds, everything holds also if D is pre-normal hyperbolic, first order. Can do the same thing. So anyway, so the main statement that we prove is if lambda mod is sufficiently small, then there are unique, advanced, and retarded fundamental solutions, denoted by R plus minus index lambda, for D index lambda, for this operator. Is, I will tell you. You will see. You will see. Okay. Support properties we have. So for ease of notation, suppose the support of W is in K times K, yeah? Where K is a compact set, compact subset of n-dimensional Minkowski spacetime. So the properties are, well, the first one says it's you have fundamental solutions. Second thing says, well, the support properties are similar, but you can have a larger support for the solutions. Moreover, so the deviation of the supports is characterized by the causal shadow of this target and source region of the operator. And moreover, if the causal shadow of the function does not intersect this target or source region of W, then the fundamental solutions of the perturbed, they coincide with the unperturbed. And of course, oops, we do have a picture. So that what I just said is illustrated by this picture. So K is the support region in the source and in the target of the interaction operator. And so you see what happens if the future causal shadow here of the support of F intersects K non-trivially. And so the future solution has potentially a much enlarged support. And of course, same thing happens if you have other non-trivial intersections. So here, the convention was actually there should be a minus here and a plus up there on the R, but convention here is to write R lambda is R plus lambda minus R minus. Okay? So applying that on an F thought to be a test function produces a solution to the equation. Okay. So anyway, so that works, and I will briefly indicate how it works. So just to say, so now concerning the lambda, if lambda is sufficiently small, then what happens? Well, then it happens that the lambda W term is just a perturbation of D, and the hyperbolic character of the partial differential equation is essentially preserved up to some perturbation. And then the R plus minus lambda can be constructed as Neumann series from the R plus and R plus minus and the W. So you write it like that, and then you see, okay, now you can observe that this operator here, because this W is a smoothing operator, C naught infinity kernel operator, in an L2 space, or even in a very general Sobolev space, this is a bounded operator. So take the operator norm, scale the lambda so that the operator norm of everything here is less than 1, and you get a convergent series in the operator norm. And so this is the value of lambda that you need. Okay, and then you check that all this is functionally, analytically nice, yeah? Yeah, you could potentially, I guess. No, this does not work for all lambdas, I think. You need some L2 estimate, and that relies on, well, I should say something more. There's a detail that I'm shoveling under the rug here. What we actually do is we put some cutoff. So what we need is that if you apply this to a function, you get something which has support here in the future. But we want to have this finite volume. Otherwise, it's not an L2. So we cut it off in time. Yeah? And then we invert it, and then we show it's independent of the cutoff. Yeah? But at some stage, we need finite volume in the time direction. And this is why we do not know if that is globally true. So our method of proof needs some finite volume at some stage. Okay, anyway, this works nicely, so you can control all the functional analysis that you require. So, okay, now if lambda is not required to be small, so you don't have it for all lambda, then this operator might fail to have a hyperbolic character, and there can, for instance, occur compactly supported non-zero solutions to this homogeneous differential equation. And we give an example in the paper. It's very simple. You take W to be a tensor product of two functions. Yeah? So one function in the X slot is W1, and the other in the Y slot is dW2. And then you arrange things such that you get a non-trivial solution which has compact support. You can do that. But in order to have that, you might be forced to make lambda large. So probably is not contradictory. Yeah, could work. So I'm not excluding that it works. Okay, so supposing that we have lambda small, and the advanced and retarded fundamental solutions can be uniquely constructed, the Cauchy problem with C0 infinity Cauchy data is in general ill-posed. So for instance, you can again take such a capital W to be a tensor product of two functions, W1 and W2, which have causally separated supports. Yeah, so that acts non-locally. And now you can arrange Cauchy data and these functions W1 and W2 in such a way that you can show that no matter how small lambda is, there's no solution of this perturbed partial differential equation which has these C0 infinity Cauchy data. So this is an example where the Cauchy problem cannot be solved. And okay, there's another related example again, where you are in this situation that you have the advanced and retarded fundamental solutions, and there's a non-zero solution which has vanishing Cauchy data on some Cauchy surface. That means in this case, even if the Cauchy problem could be solved, it wouldn't be unique. So solutions wouldn't depend uniquely on the Cauchy data. Okay. Well, this goes to show what you would expect, that for non-local in the time direction potential operators W, this partial differential equation can in general not be reformulated in Hamiltonian form, which means you write it as d by dt of u are the would-be Cauchy data, plus an operator in the Cauchy data function space, ut equal 0. So looks like quantum mechanics, essentially, where the, as I said, the u correspond to the Cauchy data of a solution at time t. So this does not work. Differential equations of that form can be solved under very, very general conditions on the A. So, for instance, if the A are non-local in these Cauchy data directions, that does not matter. I mean, you can characterize what kind of operators admit good solutions, regardless of whether they are local in the So anyway, so supposing we have such a problem and we have solutions to this initial value problem, then like in quantum mechanics, there are time evolution operators. Let's say time evolution operators taking data from some fixed initial time, t equals 0 in this case, to some other time t. And then, remember quantum mechanics, from this you can derive Müller operators by forming these limits here. So you you develop some solutions or the Cauchy data back in time first with the interacting dynamics, and then push them forward in time again with the free dynamics. And you can do this forwards or backwards in time. And then you get, if you take the limits and write down this product here, that's the scattering operator. So, well, now in our situation, we do not have these time evolution operators from time 0 to time t of the Cauchy data. So that doesn't work. Nevertheless, if there are these unique advanced and retarded fundamental solutions, what we can still do is to define Müller operators and the scattering operator. That has to do with the fact that the potential is really confined to a finite time extension. Of course, you can then later take limits, where you allow this to extend, if you want, infinitely in time. Of course, you need to have some control so that it falls off nicely and so on. Anyway, let's consider the previous situation that we had. So K plus and K minus will be regions to the future or to the past of the support region of the interaction operator. I will soon show a picture. So, and since we have these solution operators like here, this is a solution of the interacting dynamics, and that is a solution of the non-interacting dynamics. And we can, if you like, compare them, map them, identify them in the future or the past of this interaction region. So, and that's what we're going to do. So, if we were to have a Cauchy problem, well-posed Cauchy problem, then you see one of the Müller operators takes, let's say, Cauchy data here in the past of the interaction region, propagates it with the free dynamics to the future of the interaction region, and takes it there to be data of the interacting problem. So that's this purple upward arrow. From there, you, as said, take this as data of the interacting problem, and now you propagate backwards in time with the interacting dynamics. So, and that you can do here as well, even without having a Cauchy problem, because you can identify the test functions here on the regions to the future and the past of the interaction region. So that works well. And you get the scattering operator. So now what you can do is you can take the generator of the interaction operator with respect to lambda. That is, so to say, the field strength coupling scale, if you like. And then if you take this derivative, you essentially find that this gives the potential acting on a solution to the free problem. And using the R, you back it back to a solution of the free problem. So, okay, now, that's so to say the classical part. Now, think of quantum field theory. Think of quantum field operators. The quantum field operators, psi h, can here be the Dirac or Klein-Gordon field operators. This does not matter much, but depending on it, D is either, let's say, a Klein-Gordon operator or a Dirac operator. Anyway, you can show there is a, now depending on case, CAR or CCR, a star algebra morphism, which is, so to say, the C-star algebraic second quantized version of the scattering, which happens at the one particle level, so at the level of these functions. So it, so to say, does the same as at the one particle level. It describes the scattering of the quantum field when it interacts with the potential, and here it can interact with this non-local potential. So, and then you, well, get these second algebraically, second quantized versions of this first first quantized, if you like, scattering process on the solutions. So now, commutative or non-commutative Minkowski spacetime as a Lorentzian spectral geometry. I have written down here. There are some gentlemen who have occupied themselves with that. Eckstein is missing. I wrote Heller, but I meant Eckstein. I'm sorry. Okay. Suppose you have a Lorentzian spectral geometry. Suppose you would know what that is. So some people are laughing, some are not. Those who are not laughing are the ones who live in the Euclidean world. Okay, I understand that. Anyway, so this isn't working either. Why is it switched off? I don't know. Switched off probably. Well, okay. So I'm modest here, so I'm thinking of non-commutative Minkowski spacetime described as a Lorentzian spectral geometry. So here, spectral geometry, in this sense here, this very restricted sense, is meant only to refer to the space-time part. So it's not supposed to model some internal symmetries, gauge symmetries or so. It's just concerning the description of space-time as a spectral geometry. So the Hilbert space of the spectral triple are L2 spinors on Minkowski spacetime, and now you immediately notice that L2 is not a covariant concept in the Lorentzian regime. So you need to keep track of that, and you write some extra element here into the data of the spectral triple, which I have called here gamma 0. It would be gamma 0 in classical Minkowski spacetime. That tells us essentially what we have done in order to turn to endow the spinors with an L2 symmetry, to give them to give the spinor space a positive measure. Pardon? Yeah. You could also start differently. You could say, okay, we start with a Krein space, and then you need the Krein structure, which essentially is that, or its inverse. So that's practically, it's equivalent in this case anyhow. So you have some Hilbert space, you have some information in the Lorentzian setting how you got to the Hilbert space. Then you have an algebra which is in the classical setting algebra of functions on spacetime. You have to settle for some choice. Let's say Schwartz functions here. And then you have the Dirac operator. So that is really the Lorentzian Dirac operator in the four-spinner formalism, yeah? As you're used to. So then we have, as usual, other entries here. There is a charge conjugation. There's a chirality operator also sitting here. And there are intricate relations between these data of the spectral triple, and there are some functional analytical requirements and so forth. I understand they are not fully settled down for the general case. So, I mean, in this new paper by Paschke, by Cohn and Adam, they have considered the semi-Riemannian situation, and they have, well, given what is maybe at present the most general approach for this setting. But if you reduce to, let's say, just non-commutative Minkowski spacetime, you can give a working definition for this beast without worrying too much about several modifications. So I leave it at that stage. Yeah, okay, I'm coming to that. So let's consider classical Minkowski spacetime, okay? Then A is really an algebra of functions, and it's represented on our spinners by point-like multiplication. That's its action as left module or what you will, okay? So, so here we have the commutative algebra, let's say of Schwartz functions, to make a definite choice. It's not compulsory, but let's do that. So, now, here we have a potential interaction operator. This would now be with the elements in here, acting by point-like multiplication. The H is in the L2 spinners, if you like. So, and now you do this. Of course, you can, well, you can do the usual scattering, potential scattering for the potential acting by pointwise multiplication. That's completely classical, well established in the literature. And you can look at what the generators of the scattering process with respect to the interaction strength look like. And you see, well, supposing our quantum field has been given in vacuum representation, what we get is this derivative is given by the commutator of the field operator here, which we act on. And what's in here, and which implements, if you like, the generator, is the Wick-ordered square of the field. And its weight, so to say, is this element in the algebra. So you can essentially use this picture now, slightly deformed. A is sitting here. Yeah, you have a scattering process, and the scattering process, well, takes action everywhere in the causal shadow of the support of A. Yeah, and outside nothing is happening. Yeah? So, plus a stagger in some notation, yeah. Yeah, and now we would like to play the same game for, let's say, Moyal-Minkowski spacetime. So the pointwise product is replaced by the Moyal product. Like so. You could also multiply from the other side, or you can multiply from the left and the right at the same time, or you can take a sum. That's actually the nicest way to do it. Take a sum of multiplying from the left and then multiplying from the right. makes things very nicely symmetric and invariant under the charge conjugation. And there's something you would like to have. But for the moment, let's just consider this simplest case. So now, what happens then? Well, we can again consider scattering, yeah, and take the generator of the scattering transformation. And what we get is a field operator, again, in the commutator with the field operator that's been acted on. So, and that induces an assignment of elements A, which are now in the non-commutative algebra of spacetime, to quantum field operators, or operators in the quantum field operator algebra. Yeah? Now, this is important. Why is that important? Well, also in the previous case, we had a spectral triple, Lorentzian spectral triple, somehow fixed. The only difference was the algebra, because the Dirac operator stays the same, the Hilbert space stays the same, all this other stuff here stays the same. Only difference is in the algebra. Now, if we have, so to speak, second quantized this Hilbert space in order to get to the quantum fields, these psi. Right? So in both cases, same quantum field theory. Now, how do we notice that this should in fact refer to a non-commutative algebra of space-time instead of the commutative we had before? Well, it lies in this assignment, which we get here. Yeah? That I'm not I'm not saying what these operators are. Okay. They are there, and they have interesting relations, say, where in fact the Moyal-Riefel product of operators enters, or if you like, the warped convolution product of you know who enters. So, yeah. So, the information, so the message is, so everyone listen, message. The information that in this case we have a quantum field theory living on a non-commutative space-time sits, if you like, in this assignment. Or that is not only, but that is a way to find out. So, oh, it's just the same. It's the same spinners. Same spinner space, same L2 space. Just the product of the algebra action and is different. I mean, you play the same game as for Moyal planes or spectral triples. So, but nothing much changes, but changing the character of the Dirac operator from Riemannian to Lorentzian. And then, of course, you have to modify the axioms for the spectral triple. Yeah? Because then, yeah, okay, so. Yeah, okay, that is something we are going to find out about, okay? So, that's not finished. We are working on that. Okay, but that's, of course, the next natural step, to see what are the relations between the X operators depending on the algebraic structure of the A's. Yeah? Okay, so anyway, algebraic structure generated by the XA is equivalent to, now I'm saying what we think the result is that's a conjecture, and we're working on it, is equivalent to the Moyal-Riefel deformed Dirac-Klein-Gordon quantum field operator, or Dirac-Klein-Gordon field with warp convolutions. So there is a relation between the structure of observables of quantum field theory on Moyal-Minkowski spacetime, viewed as Lorentzian spectral geometry on one hand. So that's the approach I just suggested to proceed along, and the Riefel-Moyal deformed quantum field theory on Minkowski spacetime. Yeah? So you first start with the usual quantum field theory, and then you replace the products between the operators by the Moyal-Riefel product, which you get from the action of the translations on the field operators. Okay, so we believe that this is true. Okay, that's still a secret. I'll tell you next year. Yeah, unfortunately, we don't know it in as much detail as you would like to know. But I'm optimistic we're going to find out. So anyway, so just to illustrate again what the logics are coming from such a Lorentzian spectral triple, whatever that is, well, to a quantum field theory, what you do is you second quantize this Hilbert space, yeah? You take the CAR algebra of that Hilbert space, which also has to relate to the charge conjugation and so on. And you view these as algebra-valued distributional solutions to the Dirac equation with this Dirac operator, as you would for the classical case. And then you get, from the scattering, you get an interaction, which now is mediated, so interaction with the non-commutative potential. Yeah? So, and that is mediated here by such operators. You can now take them as observables depending on the algebra elements in the non-commutative algebra, which is very much the approach you do in interacting quantum field theory as well. Sometimes this is referred as Bogol-Ubos formula. And, well, then you have this assignment, and that assignment we want to find out about. Yeah? So how do we get nice commutation relations of x's with different a's and b's inside, and what happens if we have A star B inside, and so on. So that's still a work in progress, actually together with Gardner Flechner and Dorothea Barnes, so we're trying to do something in this direction, but it takes some time. Tell you next. Well, it's just, well, yeah, okay. I mean, all that you need to make this work is, so to say, the Hilbert space or some suitably dense subspace. And what you need is the R operator, the R without the lambda. That is inducing the Hilbert space scalar product, and that fixes the CAR algebra, basically. So as soon as you have that, you need not talk about Minkowski spacetime. It's just an algebraic structure which you put on top of this spectral triple structure. But that, of course, does not, as you say, no, it does not tell you that you have a quantum field theory in Minkowski spacetime. And so the question is, how do you find out? And one way is you say, okay, I take these XA operators. So in a commutative setting, we know what they look like. They give us the Vig square of the field. That is essentially the density of the field. And that behaves like a nice observable scalar quantum field embedded in the field algebra of the Dirac field. Yeah? So that is, in particular, it's an observable quantum field. It tells you, labeled by the A, where there is something sitting, essentially. Now you can imagine if you have a non-commutative A, this telling you where something is sitting is more spread out in a way. And that you find out when you compute relations between XA and XB. Look at their commutators, their products. The algebra they generate, depending on the algebraic structure of the A's. And our, well, we have calculated a little bit, looks like what you get out is a structure which is basically the same as you get when you deform the quantum field theory on Minkowski spacetime. Well, in this case, that wouldn't be surprising, but it would also be gratifying to get that out because it points at a general way how to put a quantum field theory on a non-commutative spacetime and how to retrieve the information that this quantum field is traveling on a non-commutative spacetime. Yeah? And how the observables of the quantum field theory are able to probe the non-commutativity of spacetime. Well, I don't know. I mean, this is a bit seen from the point of view, how do you get to observables in quantum field theory? Yeah, and that is usually through scattering. Yeah, so you have a scattering process, and you're trying to see where does what can you learn about the interaction, which operator is telling you. And so we sort of followed precisely this paradigm, so to say, on the side of the quantum field theory. Yeah, so I think that's the answer. So it's inspired by Bogol-Yubov's formula, as it's called, in quantum field theory, that provides you with observables. Pardon? Well, classically, you have space-time, space-like commutativity. So, well, we don't know yet. Oh, classically. It is the commutator is related to the Riefel product, but we have so far checked only in the case of commutative time, so that is probably not the same thing. Oh, I don't know. I must. We have done some calculations, but I don't recall the details of them all.
time if I were here.